Everyone doing? Pretty good. Really good. Okay. All right. No bads. That's good. Um, one more day. Full word series. No, that's what you're all really worried about. Maybe. Oh, it's automatic action. Okay. Today we're gonna finish talking about greenhouse gases and why our planet looks like this kind of, and why we don't want it to look like this. Right? Okay. You're all ready? You've been prepared? You read the lectures? Everything? Do folks prefer them in PowerPoint or would it be easier for them to be in PDF? Or do you not care? PDF, PowerPoint, you don't care. Okay, most people don't care. That's fine. Okay. Okay, you're all ready for today's class? Intellectually engaged? You interpreted everything from last time? No, not off the bat. Come on. All right, we're gonna do some thinking. What would happen to Earth's temperature if the entire planet were covered in fluffy white nitrogen clouds, but we didn't do anything to the greenhouse gases? Would the temperature go up? The temperature go down? Or the temperature wouldn't change? Everyone ready? 5, 4, 3, 2, 1. Okay. Very few people thought that it wouldn't change. Majority of folks thought that it would get colder. Anyone from the colder camp want to describe why? Yeah.
There's like what if clouds covering the sunlight, then
Yeah, so like if it's very cloudy out, they're very good at reflecting light. Just like snow is very good at reflecting light, and then it doesn't get absorbed, and the temperature goes down. So you may have noticed in Tuesday's lecture, we showed what the planetary temperatures would look like if you remove greenhouse gases. And counterintuitively, it went Earth, Venus, Mars, right? And the first one, Earth, might be a little surprising because Earth is farther from the sun. So how could that possibly be? How could Venus be colder than the Earth if you remove the greenhouse gases?
Not that. The atmosphere will still be there, right?
Yeah.
So whatever's the atmosphere is made of will still affect the
Yeah, so the same amount of clouds, right? Venus is very, very reflective, right? And the Earth has lots of water on the surface, and water is very dark, so it absorbs more light. Okay. This is what Venus looks like, by the way. Color images. Pretty nasty. Hey, it's still there. Pretty nasty stuff. We put these probes down. You can't exactly see it here, but they have this little like finger with 3 colors on it. They take a photo of that when it's in Earth's air. Then they take a similar photo when it arrives at Venus, and they can do the color correction afterwards, right? So they're all like saturated. So this is what your eye would see if you could survive. Pretty cool, right? Okay, and then we talked a little bit about this idea of feedback. We said positive feedback is not always about good things, just means that you keep whatever change that was going continuing. Right? What was the example we gave in the clicker question for negative feedback? Sweating. And sweating does what? Cools you. So you get hot, you sweat, you cool down. Negative feedback stops the heat. You get that? Yeah, we're going to use that all day today. If we don't get it, let me know. Okay. And then we talked about Venus. We said that it was as large as Earth and it had all these volcanoes, right? And so it started outgassing and it held on to its atmosphere. And those greenhouse gases that were coming out of the volcanoes made the surface warm, which led to high surface temperatures. Those high surface temperatures means that the steam that was created, the evaporation off the top of the water, leads to steam, leads to boiling of the entire ocean, and all of those greenhouse gases are now trapped at the bottom, making it 700 degrees, right? Okay. If you dropped a giant ice cube on Venus, could you save the atmosphere? No, no, it's screwed. Okay. All right. So that's what it looks like from above. It has these beautiful clouds. The Atatsuki mission from the Japanese Space Agency showed that these are like really, really high up in the atmosphere, and they're basically moving super fast, whereas the ones near the ground aren't moving. Okay. So your major question might be, well, where did the steam go? Right? Just two ways. So you have these ultraviolet photons, just like we have at Earth, but they are absorbed by ozone. If you have too much of it, it can break up the water. And after you break up the water into hydrogen and oxygen, the oxygen goes into rusting the surface and the hydrogen just escapes. And then you lose the planet's water forever. You can't get water back. We haven't yet talked about how you get water to Earth, but that'll happen when we start to form the solar system later in the semester. Okay. Where do you think water comes from? Like this water that I'm drinking? Close? Sparklets, yeah. Yeah, is it from Earth?
When you guys look into the astrobiology, like the impact of when the universe is so much that vacuum it landed on our planet, right?
Yeah. So we're gonna see a little bit later that when the Earth forms, its entire surface is molten. It's hot, right? It's got all that leftover heat. So if there was water from us forming, it immediately boils off, just like it boiled off here. So you don't get any oceans at the formation of the Earth. You have to deliver them, and the only way to deliver them is from the asteroid belt and from comets. So you're drinking comet water. Pretty cool. Yeah, it's kind of cool. Okay. Oh, not again. Another one? All right, we're going to use this idea. We're going to ask the question, what would happen to Venus if you moved it to Earth's orbit today? Would A, runaway greenhouse would reverse, leaving an Earth-like climate. B, some decrease in the temperature, but still too hot. C, the CO2 in the atmosphere would condense and fall below freezing. D, no change at all. E, a slight increase in the temperature, still way too hot. You got it? 5 more seconds. 5, 4, 3, 2, 1. Okay. All right. I didn't trick very many people. There's kind of some even distribution here, but most folks picked some decrease in the temperature, but that it would still be too hot. Why isn't this one right? Why can't we reverse the global greenhouse thing? Just by moving.
Well, the runaway greenhouse, as the name implies, it ran away, it's gone. So you can't really,
Well, the greenhouse is still there, right? And all the gases are still there. Can I stop it just by moving it? What do I have to remove? The greenhouse gas, right? The things that are making it hot. You have to take out the greenhouse gases. You can't do that right? CO2 is a very effective greenhouse gas. How much of the atmosphere is made of CO2? 96%. Okay, good luck, right? So you remove 96% of the atmosphere, you're left with what? 4% nitrogen? It's a tiny atmosphere. So we're not going to live on Venus. Don't even get your hopes up. Okay. Let's learn these ideas. Learn them good. Now, we're not going to do the whole thing today. So while everyone's still listening to me, okay, just up to problem 7. Finish problem 7, and then like raise your hand or tell me that you're done. Yeah.
well, like, you know.
Yeah.
You know, actually, where's the water?
Excuse me?
You know, when you got like the water and everything from that.
Yeah.
Where's that water?
Oh, that's from the formation flood. So that's actually created in the explosion of the giant star. Okay, let's work groups of 2 or 3, please. Get extra? Yeah. That's right. Can't wait too many today. Audrey, Omar, Gabriel, Angela. This one?
These are the questions.
Nervous, excited, yeah, something like that. We'll see.
Might have a party or something like that.
No, I'm actually gonna be at work tomorrow. Yes.
Last time we did that.
81.
Yeah, like
Yeah, quite a bit.
Realistically.
No doubt. No doubt. Bet in California. Yeah, bet in California. Oh, yeah, that's a net loss. Vegas never lose.
Well, no, I think.
Overall, the
Yeah. Yeah. This one is. I did like this one had not.
And it's a real experience. Yeah.
It's not easy.
Good?
We're not hot topic right now. Very. No. So you're just like, you know what's right, but you're not sure it's right.
Third line.
Very, very. Just because there's a thing doesn't mean. The one thing I want to ask, so let's say. There's more. It's a little bit, but. Well. This was July. Where'd you guys put it? So which one? That was. All of this. Then. All right, who's not done? Raise your hand. Not the whole thing, just problem 7. Yeah. You finished 7 and that's it. Don't keep going.
Yeah.
That's going back to.
Yeah.
Whereas. We say that there's something on the whole. That shows up the current story on. Well, we have our.
Done? Okay, folks. You ready? Another one? We just did that. Okay, well, what happened to Mars?
It was moved to Earth. With A.
you get a greenhouse effect, making a very pleasant Earth-like climate. B, it would be runaway, and Mars would be too hot. C, the polar caps would melt into oceans, leading to a stable climate. D, some increase in its surface temperature, but still too cold. Or E, nada. Okay, let's close it in 5, 4, 3, 2, 1. Okay. Okay. There's 3 answers that folks liked. No one liked no change at all. That's good. There would be a change. Folks did not like that a runaway greenhouse would develop. So there's 3 options. Anyone have a argument they want to make for any of them? Anyone who hasn't talked today? You can be wrong. It doesn't hurt to be wrong. It does? Okay, whoops. I didn't know. Oh, wait, I'm fine.
Polar ice cap melt ocean because it's warmer, right?
Yes, it would get warmer. That's definitely true. But its polar ice caps aren't very big. Now, you didn't exactly know that, but we did say that they're made of dry ice. And what happens to dry ice when it warms? Yeah, doesn't make oceans. Okay, so it's not C. And he's mostly intact. Yeah.
Because its size is so much bigger.
Right. Yeah, so because it's small, right, you're not going to get volcanoes. It doesn't have a very thick atmosphere. You don't have a new source of atmosphere. So yeah, you would make the surface a little warmer, but that's it. So if someone tries to sell you a timeshare to Mars, take them up on that? No. Timeshare is like when you like spend money and they're like, oh, this house is yours, but you can only use it for 2 months out of the year. It's like a MLM, but for Florida. What? So if you think, okay, let's go and live on Mars, we can just make it just like Earth. What's the major problem? Small. Okay, atmosphere thin. It's gonna be cold. If the solution is to bomb the polar caps, like put nuclear weapons and destroy the polar caps to put that back into the atmosphere, there's not enough air. You're still gonna die. And then that air is all gonna escape. Okay, so let's focus on the planet that's good and the one that we can solve. Yeah.
If it started around our orbit's distance, would it be the same outcome?
Probably. Because it's small, right? I mean, it probably may have been more habitable for a little bit longer. But as soon as the volcano shut off, you're basically on a downward trend down. Okay, so this is a big question. Why didn't Earth suffer the fate of Mars or Venus? Right? So let's talk about climate stability. And in particular, you've heard about the water cycle. Now the new and improved CO2 cycle, right? So if you're familiar with the water cycle, that is just like rain, and then it goes down into rivers, and rivers erode the land goes into the water evaporates, makes clouds, clouds condense. Are you familiar with that? Yeah.
Does CO2 have a water form?
The CO2 have a liquid form?
Yeah.
Under huge pressures, yeah. Yeah, but definitely not the pressures at Mars. What?
But here, it's not.
Yeah, directly, like dry ice. Okay, so we're gonna talk about the CO2 cycle. And it basically has this picture, pretty straightforward, except for instead of like the water cycle, the rocks use the magma to take CO2 out of the air and put it underneath. Okay, so here is CO2, these little white dots. They rain out. They come down in the rain, they go into the ocean. This makes the ocean full of CO2. This is great for fish. Fish love CO2, right? Or oxygen. No, algae likes CO2. Anyway, algae goes around eating the CO2, uses it to make oxygen. The number one source of air, algae. Okay, so you have all this algae in here eating up the CO2. That's a great way to get rid of it. But unfortunately, that's not enough. So what happens is this stuff sediments and it falls down to the bottom and gets put into the crust. And then we talked about the fact that oceanic crust is denser. So it goes underneath other pieces of crust and it traps that CO2 back in the ground. And the way it comes back out, outgassing. So you have some volcanoes, CO2 comes out, and the process starts again. That's straightforward, even if it's not simple. Okay, you see the loop. Outgassing, rain, yeah, better word than what I was gonna use. Runoff, ocean, sedimentation, subduction. Okay. We have just the right amount of greenhouse warming to keep life, keep water liquid at the surface and therefore to keep us mostly alive, right? And why is it the case that it's just the right amount? It has everything to do with the carbon cycle and has to do with the negative feedback cycle. Okay. CO2 is extremely soluble in liquid water. So every time it rains, it scrubs the air, which is great. And so if you ever felt like, after a nice rain, it like, oh, I feel like I can breathe so much better. It's not that reason, but it feels like it should be. The amount of CO2, remember, in the atmosphere is quite small, parts per million, right? And so oceans and rain, they dissolve the gaseous CO2, and then they put it into carbonate rocks like limestone. Anyone know what limestone is? How do you form limestone? Not from limes. What? It's a pretty countertop. Okay. How do you make it? Yeah, the right shape. So you get little diatomaceous plankton, and they take the carbon from the water and they use it to build their armor. Then they die, and their bodies fall to the floor of the ocean. And their bodies fall to the floor over and over and over, that it builds up in layers and makes limestone. It's not shellfish. No. It's a type of plankton that does photosynthesis, but creates armor. Diatomaceous plankton. Okay? Because what you got to do is you got to build your body out of carbon, and then you got to die. Why do you have to do this? You have to build your body out of carbon to take it out of the water, and then you got to die so that your body goes down to the floor, so that we can, in our little cycle, in our picture, right? Ocean. Okay, so here's the source of carbon. Carbon goes into the ocean at the top, right? Gets used by stuff in the water, and then sediments down to the floor. That make sense? It doesn't just like magically fall to the floor, right? CO2 is still a gas, just like oxygen's a gas. So they can just be trapped in the water. They stay right at the top. That makes sense? Okay. The Earth has a built-in thermostat, but it's for CO2. Let me show you how this works because this is very important. Let's take one and then we'll take the other. Let's say that the Earth is too warm. Okay, the Earth is too warm and we get a lot of evaporation. And a lot of that evaporation leads to rain. And suddenly you start scrubbing the atmosphere. All the CO2 starts coming out of the atmosphere, right? More dissolved in the rainwater. And then the CO2 concentration goes down. And the temperature gets colder. What type of feedback is that? What was that? Negative. Negative feedback. All right, let's look at the other way. Let's say it's too cold. Okay? Then you get less precipitation because you get less evaporation from the oceans or lakes. Okay, so that means that you dissolve less CO2, so it starts to build up, and the greenhouse gas makes it warm. Then we go in the other direction. Perfect. We solve climate change, right?
Yeah.
Yeah. Okay, how long does it take? 5 days, right? Yeah, okay. Okay, so let's ask a different question. And this is related to something that we saw earlier. So go ahead and think back to the ideas that we saw. Okay, suppose the Earth entered a major ice age and the oceans completely froze over. How would Earth's atmospheric temperature change while the oceans are frozen? Would A get warmer? B it get colder? C stay the same? Impossible. I don't know why you made this question. Okay, we have 2 camps so far. Put your vote in if you haven't already. 3, 2, 1. All right. So some folks say it'll get warmer. Some folks will say it'll get colder. Ask your neighbor. Convince them that it'll get warmer or it'll get colder, depending on what you believe. Don't be reasonable. Don't listen to them. Don't learn.
Yeah.
Okay. Try it again when you're ready. No one's mind got changed? Five, 4, 3, 2, 1. Interesting. What did you guys talk about? No one's mind was changed. Like literally the same number. God, you listened so well to not listen. Okay, so a lot of folks liked warmer, a lot of folks liked colder. It seemed like that was pretty easy. There's no water for humidity to make it warmer. That's fun because that uses the idea from Tuesday, right? The idea of like, if you don't have water to like trap things down. Let's think about this in the context of the climate cycle here, thinking particularly about CO2. So not daily changes, but say yearly change. Let's say that all of the oceans freeze over. Less evaporation, which means no rain, which means right. So what happens to CO2? Goes up. Right, if there's no way to get rid of it from rain, and you start building it up, and the temperatures get hot. What? All right, counterintuitively, the temperatures go up. Okay, I can show you a picture of this in a few seconds. Okay. So we'll get to this idea, the snowball Earth, in like 4 slides. I promise. I promise. This has happened here many times on Earth, not like in LA. Okay. So why did Earth retain most of its water? It's big, right? That's the big one. The biggest of the 4 terrestrial planets. It happens to sit at the right location. Now, there is a range of acceptable distances. So for example, we'll talk about snowball Earth, which has happened at our current distance, where it got too cold for liquid water, and the entire surface of the Earth is frozen. Fun, right? Okay. But we have the right combination. And so let's say we were to start talking about how to build planets and thinking about atmospheres, maybe on this thing called a homework. You would now have all the tools to build the perfect planet, right? And if I told you how to break one of those, you would be able to tell me what it would do. Okay. So why does the Earth have so little carbon dioxide, but Venus and Mars are almost entirely carbon dioxide? Yeah.
Oh, does it like earth trees absorb the CO2?
Yeah. So did you know that the Earth started off with CO2? And one of the first mass extinction events was life getting way too good at doing what it did. And all the oxygen in the air is due to life. And if you kill all the life, you go back to CO2. Yeah.
Is that what we have like your amounts of oxygen back then?
I think the oxygen concentrations have shifted as a function of time. I don't know whether one drives the other, or if you're, taking advantage of the fact that, like, for example, there's a lot of continental crust versus oceanic crust, and that distribution has changed over time as well. As you guys know about Pangea. Oh, I already said that. Those are not the words that go with that statement. Okay, let's talk about snowball Earth. Millions of years ago, and we have geologic evidence for this, right? There were glaciers at the equator. There were glaciers certainly in California. You know where the glaciers in California that I'm thinking of are? Evidence for them, they're not currently here. Which valley? No. No, this is actually a tectonic valley. So this is from the fact that you have volcanoes on one side and a fault line moving the other direction. Glaciers, remember, they cut through mountains. There's a famous Californian location where you only have one half of a mountain. Half Dome, right? Famously cut in half by a glacier only a few million years ago. And so apparently, for no reason of our choosing, Earth got real cold like, and the ocean froze. So what happens when the oceans freeze? You reduce the precipitation, you increase the reflectivity, and it gets really cold. right? The reflectivity, oh, I already said that. Why aren't we still frozen? CO2 comes to save us. Okay. Here's the example. Here's growing polar caps. Here's outgassing. That's not Earth, obviously. You know what I'm saying? Example. This is a snowball Earth. The whole thing freezes over. The frozen oceans stop the CO2 cycle. So now it starts to build up. And the atmosphere gets warmer and warmer and warmer until you fully melt the Earth. It's too hot. And then the CO2 cycle restarts. You put the CO2 back in the oceans and you reduce the greenhouse effect. That's fair? Yeah. We'll get to that. Okay. So first we have to explain how it should work. And then we'll explain what's happening. Because they're not the same. Okay. This is a different thing than positive feedback from Venus's atmosphere. That was a runaway greenhouse. This is a controlled greenhouse, right? The cycle back to where it started. So we're happy with this one. And in fact, the Earth would be perfectly fine, right? We will not be fine, okay? If it gets too hot, right? If everything's melted like that, you're gonna have a bad time, okay? Let's see. This is another picture. I guess this is a different way of looking at it. So we've had a stable climate for a really long time. We look at the historical record for like the oldest microbes we can find, and it's like as soon as the Earth had a crust that had water on it, you basically find single-celled microbes. You get unicellular life within the first billion years, which means that we've had a pretty habitable planet for almost 3.5 billion years. So if you think about that, this cycling back and forth has been working a really long time. Now, is that the, is this idea here, right, which has happened before, is that great for life? No, right? Kills lots of things. The reason that we are mammals and not reptiles has everything to do with our ability to survive one of these. Not us specifically, but right, little shrews. Okay. Okay. It takes this long. So if you fuck up the climate, you have to wait 400,000 years. I am not going to get that old. I don't think you will either. Okay, as much as those vitamins help. So here's all the reasons why the Earth is habitable currently. The geology, right? Plate tectonics and volcanism are the reasons why we have outgassing. They're the reasons why we can use the CO2 cycle, right? By taking that material, and the plate tectonics allowed us to put that CO2 back into the Earth. We need water in order to do that. We need water in order to breathe. One of the major reasons we think Venus is not habitable is because its crust dried up. And once the crust is all dry, it can't split under other crust. Okay? So you have to have hydrated crust in order to get them to move. So you need water, probably for plate tectonics. Venus lost its water, it lost plate tectonics, runaway greenhouse. You need an atmosphere in order to be habitable. We love that. We love breathing. That's really important to everything that we know about. You need a stable climate, something that's not running away or escaping. And life itself will help. So the very first life, CO2 was the abundant gas on Earth. And we can see RNA life was extremely successful and then basically just killed off all of its peers by creating a poisonous, toxic cloud called oxygen. And then the rest of the microbes were like, oh, I can eat this too. So they just adapted. Pretty cool, right? Okay. And here's how they're all connected. Sorry, I know these are all supposed to go separately, but that's just the basic idea. So you can see that geology, right here, connected to life, connected to water, connected to the atmosphere, connected to the climate. Okay. And these are all due to this beautiful combination of being the right size so that you have volcanoes, being the right distance from the sun so that the water is liquid, Rotating at a sufficient rate that you get day-night cycles, for example, right? And average out some temperature differences. Okay. Questions about this idea? We talked about this. What if you move Earth to Venus's orbit? You're going to make it hotter by about 30 degrees. The greenhouse effect that's already going on will start. Okay. That temperature here will go crazy. The oceans will evaporate. Once the oceans evaporate and the carbonate rocks decompose, you would make Earth hotter than. Yeah. Okay. So let's ask one more question here. Climate change real? Let's be serious here, you know? Don't do C. C is not the answer. I just want to know who I'm dealing with. Okay, I'm trying to get feedback. You can be honest. Like, I can't see what you're answering. Okay. All right, next one. Okay, this one has a little bit more. Okay, all right. So let's find out. Let's find out. A lot more folks who don't, not so sure about the second one. The Earth's climate is definitely changing. We can all see evidence for that. But have we done it? That's the big question, right? Okay. So let's think about this idea. We've seen that the Earth goes through these natural CO2 cycles, and maybe that's what we're doing. Okay, that seems reasonable. I have stockholders to appease, right? So here is the past 400,000 years. And this is us now. This is a long time ago. And these are those climate cycles I just told you about, right? Back and forth, back and forth. And this is the temperature change relative in the past millennia. So up here is 0, right? So this is the last millennia, a couple thousand years. And then that's the average, and it goes way down. This is in degrees Celsius. Someone can convert that to me, but I think it's like 8 is like 20, 15. Hot or cold, depending on which direction you go, right? Okay, so it was a lot colder, and then it was like comparably hot, and then colder, hot, colder, right? Seems fine. Natural for life. Right? Okay. Here's the updated version that shows us today. This is how the temperature here relative to CO2 that we see in ice. So you can go down to Antarctica and you can drill into the ice and pull out ice cores. And you can look at different layers in the ice, and there'll be layers in the ice from sedimentation. So snow will trap. Remember, we just talked about trapping CO2. So you can look at the concentration of CO2 as a function of time. So that's that on the bottom. That's 1750, and that's today. So that's a big jump. Okay, that's a little weird. But that's fine. It doesn't look like it's having that big a deal, right? We're chilling. Right? Okay. So CO2 concentrations, they're rising. They're 30% higher than ever before. And actually, that's not updated. That's from 2016. So I forgot to change that number. That number is bigger. Okay. Does temperature depend on CO2 levels? Yeah, right? It should. Okay. Why don't we measure the water vapor instead? We said that was a more important greenhouse. Well, we said that what I meant by that is there's more water vapor and it's better at its job. So why do we always whine about CO2 and not water vapor?
Stop the water from evaporating.
Yeah, because the water vapor is there already. We produce CO2 because we got to get to work, right? So one of them we have control over, and the other is natural. As the planet heats, you get more water vapor. So if you're trying to understand what might be driving the heating, it's silly to use the thing that is happening because, right? Water vapor follows the temperature; it doesn't lead it. CO2 leads the temperature, doesn't follow it, right? If it gets hotter, there's no natural source of CO2 that's going to come out of the ground. The source of CO2 naturally is volcanism, right? It has nothing to do with the atmosphere's temperature. Whereas water vapor has something strictly to do with the atmospheric temperature. Does that make sense? Okay. What? No. No. We are so not good. Okay, so we see this wonderful correlation, right? And the reason we see this correlation is like CO2 goes up and down, and we see that climate cycle. We see that, and we're like a little worried, you know, like that's a little bit higher than most folks think it should be. Here's the average global temperature. Again, I told you I made these slides in 2016. I updated this one today. So here's 20, let's see, that's 20, 1990. Yeah, that's 2010. Okay. It doesn't look good, but you might look at that and you might say, well, that's, you know, that's like woke, right? Like you could draw that line anywhere. So the question is I made this in 2016 and I made a prediction that it would continue to get hotter. So what would the next 8 years of data have to show in order for this to be a random thing as opposed to a trend? It has to go down, right? If it went back down, then it would all be a hoax, right? And if it went up, oh boy. Okay. Ooh, yikers. Okay, so it's going up still. So that's unfortunate for that. Yeah. So the last 8 years since I made this are the hottest 8 years on record. What did I say in the last one? The last decade, when I made this in 2016, was the last hottest decade on record. Fuck. Okay. So that doesn't look good. And remember that these thermometer temperature data, this is real data. Because we've had thermometers in the 1880s. So we've been watching. Okay, all over the planet. Now these are global means, right? Sometimes you get a little bit, it's hot, and then it goes back down. Then it's hot, and then it goes back down. Okay, that's okay. We like it to go up and down. That's totally normal. That's not normal. So you can make models, and you can see, well, what's the human contribution? Okay, so I want to show you what happens when you account for volcanism, or you account for the fact that the sun is changing its intensity and being more, it's like expending more stuff. That's the blue line. Goes up and down and up and down and up and down. When you add in humans, you get the red line. And this was from Fits the Data in black. Yeah, so it turns out that it might be us. Okay, let's look at more data. Here's what the models predict will happen. Yeah, so right now that's 2020. There's still data. This is when I made the plot. And then we're here-ish. Okay, so it's a wide range. Now you're thinking to yourself, 1 degree. I knew 1 degree. It's like 10 degrees from here to the beach, right? What's 1 degree? Remember what we talked about, even when we were talking about hurricanes. What's the source of energy for the hurricanes? Heat from the water. So if I raise the temperature of the water by 1 degree, what happens to the hurricanes? They get stronger. Okay, so that's not great. What about coral? So I know I'm only talking about the water right now, but we'll get to other things. Coral is very temperature sensitive. Turtles, for example, the temperature of the egg will give the sex of the turtle. So you could kill off all turtles by raising the temperature too high and making all the turtles men or women. I forget which way it goes. Okay. So this was in 2016. Let's look at modern data. Okay. Here's a nice range. That's us. You are here. Okay. And you have some choices, when you go to buy stuff. You can buy high, buy intermediate, or you can buy low. In all three cases, emissions basically continue to go up, right? No one thinks that you'll just stop being able to use emissions tomorrow. But if, for example, we were in the Paris Climate Accord or anything like that, maybe you could do one of these, like an intermediate. Yeah. Is there a question?
I had a question and I thought about it.
Okay. Currently, the best estimates are somewhere in here of what we're going to end up doing over the next 100 years. So these are long time scales, right? So like, I don't have to worry about it, but like your kids might, right? Okay. And what does that do to temperature? Yikers. Okay. So here's the range of temperatures that could be. We're just right about there, somewhere in between 7 and 3, probably 5 degrees warming. That's not so bad, that'll make California like the equator, and it'll make Portland like LA, and Florida will be gone. Which you can feel any way you want about that. And the reason I say Florida will be gone is because the polar caps will melt completely, and the sea floor will be fine, but the sea level will rise. The sea level rises, and you flood all those areas. Anything that's 100 meters, that'll be underwater. And then anything that was being held down by ice, so the entire country of Iceland has a glacier on top of it, and as that melts, that will release the pressure on the top of the volcanoes that it lives on, and it'll just go bye-bye Iceland. So it's not great. Not great. Okay, hold on. I got you for 2 more seconds. Greenhouse effect is going to increase with CO2. Come on now. The weather will distribute the temperature changes very unevenly. So we don't say global warming anymore, we say climate change. Because essentially all of our models predict, we talked about England, how great it is to live there, even though it's at the same latitude as Canada. But if we turn off the circulation of heat, or we change it dramatically, England and Europe may become as inhospitable to life as Canada. Also not great, there's like 600 million people live there. You get increased evaporation from oceans, which causes more intense storms. We've seen that year after year. Almost every year, they're like, this is the biggest hurricane that I've ever seen. And you might think, wow, it's kind of boring to keep saying that. Well, unfortunately, it's going to keep happening. Polar ice melts, we already said that. Coastal regions. So yeah, this is a great idea. So you just buy a house that's like 100 meters north of the shore, and your great grandkids will have lakeshore or beachfront property. Right? It's an investment opportunity. And of course, all of the ecosystems will begin to collapse. Now, one thing that I said earlier is that a lot of the air you're breathing comes from 2 places. One is algae, and algae is very temperature dependent. And the second one is, which ones? Yeah, the Amazon is one of the major sources of air that you've ever breathed. You can watch these maps on NASA. They have CO2 maps, and it's really beautiful. You can see the daily breathing of the planet as it like sucks in CO2 and lets out oxygen, which they can track with satellites. And you can see all of the Amazon forest breathing, like literally breathing. And if we kill all of that because it gets too hot, this one, CO2 will go up, right? So, okay, so you may be talking to your uncle at Thanksgiving or your aunt, probably your uncle. And they'll say something like, well, the climate's changed before, cycles of warm and cold, this is just a cycle. So what do you say? Cycle hasn't changed this bad before? Okay, I like that one. Yeah. Yeah. So humans are now the dominant force factor. Same argument, right? We've done this before. I don't disagree. You always got to give them a little ground. Like, all right, here's a beer, and also like let's agree on some things. Okay, next one. CO2 is just a trace gas. It's a very, very small component of the atmosphere. He's done his research. Right? What do you say?
If we make more of it.
What?
Not if we make more of it.
Not if we make more of it. That's a great retort. I do like that one. That's not what I would say. Yes, it is true that it contributes a trace amount, but it creates 31 degrees of change. Right. Small. Remember, that I told you that at the beginning that this blue one is a little weird that it's in front of the Venus one, right? If you get rid of the greenhouse gases. But remember, Venus is more reflective. So the Earth absorbs a lot of heat, and we are here. That's a 31 degree difference. Just from CO2. You get rid of the CO2, you get colder. You increase it, you get warmer. Okay, next one. Well, the sun's gradually getting warmer, so this is why it's getting warmer. It's very natural. So let me have my big truck. Right? That's a good one. Can't fight that. Parts are fun.
I am right.
Right. No, okay. So in fact, the sun does have cycles of getting hotter and colder. We are currently going through a colder trend. So the sun has actually been getting less intense in the recent past. So it's not the sun's fault. Okay. The scientists don't agree, right? It's impossible for scientists to agree on anything. What do you say? What? Good, I like that one. That's a good one. Anything else?
That it exists.
They agree that it exists, and they agree that
That's bad.
it's man-made. 97% of scientists agree, okay, that it's humans causing climate change. There are no national or scientific institutions in the entire world that disagree. There are people who make a lot of money trying to sell you the idea that it's not humans, that they can continue to pump oil, they can continue to do things exactly how they would instead of investing in renewables. Now, hold on, before you all leave, this is really important. You say to yourself, well, this is bleak, really fucked up. What am I going to do about it? Yeah, it's November.
Low.
Now, hold on. Let's think about this. As Californians, you may think your vote doesn't matter. Who do you vote for? I'm not engaged in politics, that and the other thing. Find out who your local politicians are. Create community, right? Drive change locally. Yeah.
If you registered to vote and you got your ballot in the mail, there is a drop-off box right in front of you.
Good. That's perfect. If you're registered to vote, you should probably be registered to vote. If you don't care about politics, just remember politics cares about you. If you don't care about the planet heating, don't worry. You'll die.